Okay, sounds good. Cool. Oops. Yeah, so today I think my talk mainly the title is trying to make it, more grandiose, but it's like we really feels like, the future of biomedicine is agentic. Like in 10 years, maybe every biologist will have a team of agents just working for them, and then just get a lot of tasks done. And scientists just need to focus on more interesting, like on more discovery side of things. So this is a joint work done with amazing set of people, especially Yuri and also Serena, Hanshan, Jerry, Minta, Ying, Ryan, and our advisors and so on. So I want to very, very quickly give some motivations of why we're doing this. Why is biomedical agent very important? So first of all, as you probably all know, biomedical research is like fundamental across many in industries. But we're seeing that the bionic progress is it's partially limited by the lack of ideas, but it is also fundamentally limited by the human bandwidth, because there's only just a few number of like like a limited number of scientists in the entire world. But increasingly, because of the new technologies, there are like petabytes of new data just coming out every day. And when we talk to many scientists, they're like in their lab, they have like 50% of data which is left unanalyzed. It's because they don't have people to analyze it. And also, part of the reason why is that case because performing this analysis, performing this biomedical research actually requires a very complex workflow, and each of them just takes a very long time and costs a lot. And so this way, gradually, we can observe this kind of a big gap between the supply of the biomedical expertise and also the demand of the biomedical expertise. And this big gap kind of asks for a complete new way of doing science in some sense. So we need a new way of kind of scaling the biomedical expertise. So this so but we can just not make a new science, right? Because training a skilled scientist is expensive, slow, and constrained by education and training infrastructure. So we need to fundamentally rethink how to scale scientific expertise. And we're able to see in other domains, people have successfully done that. In coding, in legal, also in like web search. We're thinking, can we extend this successful success from other domains to biomedicine as well? So for LLM agent, what it basically does is giving it has a LLM call. It has an underlying the reasoning engine, which is the LLM. And then when human gives the task, the reasoning engine will kind of proactively perform some actions. And then we also have an environment that can get feedbacks based on this action. And then the reasoning engine will just keep reason about it, perform the action, and then just get feedback, and within a loop, it will stop automatically once it feels like it has answered the human's request. So we think the future of biology is agentic. The goal of our research for the past 2 years have been to create a virtual AI biologist that automate biomedical research so that we can perform tasks much faster, tackling many of tasks at the same time, and also you can suggest and explore novel hypotheses. So we were talking about how to build this kind of AI biological agent. And as I briefly hinted before, like, in the future, we're thinking a biologist is augmented by AI. It's like a, cursor. You now, like a single software engineer is actually have equal capabilities of an entire software engineer team. Um, and also we're also thinking about using agent as a way to democratize knowledge, making it universally accessible and reducing barriers. Um, yeah. So now I think so that was kind of the motivation, and now I'll delve into how do we really build like AI biologists. So if we take a more global picture of how this biological research being done today, we kind of summarize into mainly two stages. The first stage is generating a hypothesis. So like a biologist, you can say, this is a hypothesis. I want this gene causes tail loss. And it's still a lot of reasonings, like, and also running a lot of analysis and so on. There's a lot of individual tasks that are involved when you generate a new hypothesis. And similarly, when you validate a hypothesis, it's also, about statistician or the reason why this variant could cause a phenotype. You would run a lot of statistical analysis. You can also run some targeted well experiments to test if this variant or gene really make the tail disappear. So, so when we kind of look at the global, like high level picture, we think it's like a two levels of things. The first one is the outer loop, which is a hypothesis generation and hypothesis validation, and the knowledge that is kind of obtained from when we're doing this hypothesis validation will inform the next step of hypothesis generation. So we call this outer loop, and within each step, it involves a massive number of individual workflows. So these are tasks like performing some bioinformatic analysis, performing some database queries, and so on. And so this also directly translates to a recipe for building AI biologists. We have an AI agent system. Want to build an agent system for hypothesis generation. Also want an agent system building for hypothesis validation, and also a generalist biomedical agent that can perform a wide range of different biomedical tasks. It will power do the generation and validation process. So today's talk is basically following this kind of a overall paradigm. We will use so I'll introduce Biomni, a work that we aim to tackle this generalist foundations, and we'll also show that it can already be used to generate hypotheses. And then we'll also introduce a specialist distance for hypothesis validation, which is called a popper. Cool. So let's delve into Biomni first. Yes. So again, shout out to all my amazing collaborators who made it possible, especially Serena, Hanchen, Jerry, Minta, um, and also our entire team, and also our advisor, especially Yuri. So if we look at the biomedical research, we can actually abstract in a way as a reasoning plus actions. It performs some reasoning, it will do some stuff, and it gets back the result and do further reasoning. And we know that there's a lot of progress in reasoning, but in biomedicine, the action is actually not defined. And we're saying the action is probably the fundamental kind of bottleneck right now, where the current agent cannot perform real research tasks. So current agent can perform a lot of question answering tasks, but not like real biomedical research, because it does not have the action. It does not have the, I know, like if you're a scientist without hand, you just keep thinking, right? But they cannot do stuff, and then get what you observe from the experiments. So that's kind of intrinsically a limiting factor to build a AI biologist. So another way to put it is like basically we don't have an environment for biomedical AI agent. Um, Agent is not compatible with current biomedical actions. So there's no interface to link these actions to the LLM. And also biomedical actions are just like so many, numerous, diverse, and specialized. So our goal is to build an environment. So that was the most immediate kind of kind of steps towards that AI biologist vision. So when we try to want to approach to build an environment, the first natural question becomes the biomedical action space is very large, complex, and scattered. Like how do we unifiedly create an action space? So we introduced another agent. We call this an action discovery agent, which is basically for each bioarchive subject. Within each subject, we identify 100 recent published papers. And within this 100, each paper, we asked another agent, which is a LLM that reading through papers, like a literature agent. It will in that LLM, we ask it to pass what are the necessary tools, what are the necessary softwares, databases to reproduce the result in the biological research paper. Because the idea is like if we can implement all of these tools, in the perfect setting, then we can theoretically let our agent reproduce all of this paper, like all of these research results for in the past a year or so across all the 25 subjects of bioarchive. So that's kind of the a claim, right? It's not real because implementing action is like very complicated. But I think this is where we can really map out the entire action space for biomedicine. So yeah, in the
So
end,
I have a a quick question here.
Yeah.
How do you deal with tools that are so common that they're almost implicit, right? You know,
Hmm.
when I say I've run logistic regression on
Yeah.
this,
Yeah.
it's not often that I'm actually referencing scikit-learn, right?
Mhm.
So I wonder if you ran into any issues like this.
Hmm. Yeah, so so basically in our setting, we there's a it will generate so much tools and different kind of stuff. Um, but we also did a lot of filtering. We just focus on the tools that are first of all relatively popular, and then the second thing is it should be super specialized because if it's something like this like linear regression, I think we just let the LM just do it on its own. We don't need to define a tool because there's just so many of these hidden implicit tools that everyone knows. Um, but I don't think we need to define a new tool just for that because as you mentioned, then there's like just so much different packages, just different so much ways to do it, and it requires a lot of flexibilities in some sense. So that's why, as I'll talk about later, we when we design this general purpose agent, we try to want to make sure that um, you know uh, a lot of things can just be covered by the LM knowledge, and then the only thing that we bring to the table is just the specialist tool. Yeah,
Yeah, that's great. I love it. It's a non-problem, right? If it's implicit to me, it's implicit to the model. We have
definitely.
one question in the chat that I wanted to bring up, which
Yeah,
is about the review or I guess peer review of the papers. So you mentioned here that it looks like you say recently published papers. Is that they've been put up
yeah.
on bioRxiv or that they've actually been put through peer review, now they're in a journal?
Yeah, these are all peer-reviewed and published papers. So we,
Okay,
we did a lot of filtering. Yeah, so these are all peer-reviewed.
thanks.
Yeah, but there's also like people are interesting questions like, are this recent published paper a representative kind of set? I think that's an open question. Like, um, because I think there's also people say you should just find 100 kind of landmark papers that covers a lot of things. But I guess arguments against that is like there's so much new tools, and if you want to do research today, it's probably not relevant for a paper that's published 100 years ago, right? So I think for the current version that we have right now, it's an initial version to basically create a recipe to build this first action space. But in reality, we can try a lot of things when we build the next version of the environment. Cool. So Biomni, so E1, which is E stands for environment. So after we filtering a lot of things, we built the first environment, which is called Biomni E1. So it's a single environment with diverse tools, software, and databases, and it's also bridging across subfields of biomedicine. Um, so for the past, I don't know, for the first 6 months of the project, we have 5 people that just basically implementing a lot of things. Like it's like a lot of engineering efforts, but we just focus a lot on just implementing a lot of functions. So now we have around 105 softwares. So this include like ScanPy, BioPython, scikit-image, these popular biology Python packages, and we also include um, like um, sorry, let me try to find like R packages like DStick2, and also like Serute and things like that. And then also we include like bash scripts like plink, Homer, BWA, and so much and so on. So it's like so these softwares are like really popular software. So LM has already how to operate on these softwares. Um, so we just include that as the softwares. We're not specifying specific tools for them. It's just softwares. Um, and then we have this 59 databases. So each database is coming from, for example, like Nomad, Open Target Genetics, BindingDB, AlphaFoldDB, Cell by Gene, and so on and so on. So I think for these databases, there are like mainly two categories. The first category is like the databases with web API. And for that, we just need to have ask let the arm to write some simple line of code to query the web API. And there's another set of datasets database that does not have web API. And for that, we just have a local, we call this a data lake that save every raw pandas data frame. So yeah, so together we cover like around 59 popular databases in biomedicine. And then
How
lastly,
structured how structured did the databases have to be in order to incorporate them here? Because I'm looking at most of these look like at least I'd say like a tier two database beyond just like the initial sort of deposit, right? So something like I'd say
mhm,
it's like a tier one is like the gene expression omnibus, right? You just throw whatever you want in there. Um,
yeah.
does it have access to resources like those, or does there have to be some level of
Mm.
curation so it doesn't have to make the code linkers kind of every time?
Yeah, so we currently we also support like the geo stuff so you can download the data sets from the geo directly. There's a database function for that. Um, but indeed, it's like I think there's different level of granularities. I would say that as long as the format is not like crazily like historic, it's like then it's probably fine. Uh, so I think currently, at least from what I observe, it's like a lot of the geos and a lot of the raw database, the agent can process it pretty nicely. Um, but when there's becoming like some, I don't know, like some JSON files and these kind of stuff, like with very, very complex nested structures, the agent have no idea what's in it. So it requires some back and forth to figure out what's in the data. But that's also usually pretty feasible after a few iterations. Yeah. And then we have around 150 biological specialized tools. So these are like specialized tool that is very hard for just to write on its own. Um, so this include like, for example, wet lab experiments, where the wet lab could be some experimental protocols that we just get from our collaborator lab, like their internal protocols, basically. Um, and then we also have like AI models like DiffDog, UCE, um, and so on. And also some specialized know-hows, like if you want to predict like ADMED property prediction, if you want to do like some primary design. Yeah, so we define this specialized tool as the ones that are, really hard to implement by LM, which are usually correspond to some knowledge that is implicit, or you could usually require some tools that are require maybe like few thousand lines of code. Then you should just use a tool for it.
So, quick question, actually, two questions. One, I don't see benchling or anything similar, and you talked about wet lab. Are there any tools to query experimental covariates and experimental variables for each experiment that was done? Especially, again, cross all experiments is hard, but for example, let's say if this is going to be used in Genentech or other companies that rely on these, tracking tools for experiment registration and they
Mhm.
will be fundamental to get that data as well. Are there any agents to query those type of databases?
Yeah, this is actually on our to-do list right now. So we are basically I'll talk about it later when we build this kind of a web platform. We do see
Mm-hmm.
a lot of different kind of user demands. Um, and then one of them is definitely we want to connect to our own internal benchling datasets, and then we can
Exactly.
basically create a function basically for that as well.
Yeah. And this would be extremely useful because typically people have to guess what variable introduced the batch effect. But this type of agent can query all variables available automatically and find if any of your variables, time of the day, user that did experiment, all of that did an effect. So
Mm-hmm.
that's very useful. Another question I had is that a lot of these workflows are driven by, I don't know, techniques. Again, back at Institute, it was with Redon or Nextflow or some workflow because, again, especially in longer ones, you don't want to redo everything when you want to change a parameter. In the back
Mm-hmm.
end, are you using any of those basically data flow versioning and making sure which
Mm-hmm.
node in the compute graph you have to recompute?
Yeah, so currently we are because we want to build a general purpose AI agent that can perform basically any kind of a task. So we're not relying on pre-specified workflows like I think Nextflow, right? Yeah, and then So our assumption is that the LLM already knows a lot on how to perform the task because it reads every internet. Um, but I think indeed we also observe that there's several tasks that kind of require a lot of subtleties. You know, maybe this step has this kind of a parameter. You should at this threshold you should use that way or another way. So I think these requires more kind of a rigid kind of a pre-specified workflows. And for that we are thinking about basically building another we call this like task template or something like that. Um,
Yeah.
basically guide the agent to follow that task template.
Yeah. I mean, there are the two sides to the question. One is the
Mm,
template that you mentioned, which can be done with prompt engineering or other techniques as well. The other is data caching and basically tracking, oh, I want to do the same type of analysis with many different tools that are only
mm,
different in the last stage. So
mm,
I basically store the compute graph to avoid basically recomputing things that are already done, which
mm.
is fairly common in larger workflows. That's what I was the second part of the question. If
I
there's
see.
any plan to, especially as we try to employ these for large
Mm,
scale compute, we want to avoid redoing the computes that are,
mm.
already the same data going forward, even I change the downstream tool that I'm using, right?
Yeah. I think that would be really amazing. And that require probably lots of engineering efforts right now. So currently we are basically a relatively simple. It's like given a task, uh, the agent have a kind of a state that just process the request, and once the entire kind of execution is finished, the intermediate variable is kind of gone because yeah, it's just the simplest way to serve the web platform right now. But maybe in the future we can figure out some way to like maybe the user can continue to work on the session, for example.
Exactly. A lot of interesting directions to explore. There are two questions also. Do you want to go through them, Caleb, or should I?
Yeah, sure. So um, there's a question about the availability of cheminformatics resources in the Biomni
Mhm.
E1 environment, right? So this
Yeah.
is lots of very nice things for genomics and single cell, but they're asking specifically about thermodynamic properties, Gibbs free energy, solvation energy, pKa, or plans to integrate
Mm.
these resources like PubChem, Chembl, and RDKit.
I see. Interesting. Yeah. So we currently already support an Articate as the one of the software. And we have several specialist tools that there's some very basic kind of pharmacology and like for example predicting ADME property predictions, and also have some simple ways to compute basic molecular properties using like RDK basically. But indeed we don't cover a lot on like PubChem and Campbell. So that would be something that we'll be interested to do. Um, yeah, so that's part of the reason why we also want to do this open sourcing. Because I think just for the E1 that we carry now, although we spend a lot of time integrated, but the entire action space is just so large. Like it's impossible for us to make like map them all of them by ourselves. So that's why I want
Exactly.
to create a standard kind of a platform
Interface.
where people can contribute tools, databases. Yeah.
Yeah. Is there going to be a central database to probably push these? That would be probably best. I
Yeah.
think there was also one other question about multimodal data to ask how Biomni integrate and interpret multimodal data, that being genomic, clinical imaging in one
Mm.
workflow. Are there any current versions that do that type of analysis?
Yeah, exactly. So I think if we talk about multimodality in this kind of a biomedical modalities, then
Hmm.
definitely we have so it can already run like single cell analysis. It can if you give it a table, give it like Excel sheets, it can also run some data analysis on that Excel sheets. And also for the images, we also have some software that can process images. But we're not like feeding the image as the raw input to the LLM as this kind of a multimodal right now.
Hmm.
But there's indeed like tools that can process images like Scikit image, um, and things like that. But
Yeah.
we do want to we're actually experimenting right now on this multimodal features, because
Hmm.
it's actually pretty simple to add this multimodal features. Um, but yeah, but we want to see how the performance will look like before we kind of release it. Yeah,
Yeah. Very good. Thank you. I think we are good with questions, so we can
awesome.
follow. Thank you.
Great. Yeah, great questions. Yeah, so this Biomni E1 we have the kind of this is the foundation. And now the question is, how do we really design an agent that can utilize this environment really well, and then it can do a lot of crazy things in biomedical research. And so we kind of we built a simple agent to do that. And I guess we have tried gazillions of different ways, but in the end, it's just the simplest, like not much structure, just like the simplest, just works. So the first step is definitely retrieval because the environment is massive. It's impossible to put every single items in the environment to in the LLM context. It just costs a lot of tokens, and it's also just not that does not make much sense since each task only requires a very small set of tools. It does not require like 200 tools to solve a task. So that's why we have a this is retrieval step, which it will retrieve relevant software packages and also the databases and also the specialist tools. And we experiment on a different kind of way to retrieve the resource, and we find that the embedding-based approach really fell very bad. And that's why we use a LLM-based tool retrieval, where the prompt just takes the tool description and the user task and outputs the set of selected tools. And then after we retrieve it, we just append it to the system prompt, and then you can do reasoning. Basically, given task, we asked LM to do a planning, to generate a detailed plan with bullet lists on how to resolve their questions, and also the plan is tracked along the entire process with this kind of adaptive replanning. Like once we probably did some errors, then you can update the plan. And then lastly, I think this is what the most kind of changes that we introduced. It's basically we're using coding as a way to perform actions. So I think there's several motivations. The first one is like because we have software databases and pre-specified tools, and the software is like we just let the RM know that you can run the softwares, right? We're not pre-specifying a lot of the tools for the softwares. And so the question is, how do we interleave software database and pre-specified tools intelligently? Um, and if you use the classic like React or like this kind of function calling approach, it's kind of a tricky. I mean, you can of course define like a like a function which is like writing Python code, but it's just a bit kind of complicated and not natural. And then and another thing is like we also want to compose more complex logic. So if, for example, for some specialized tool, we want to do like a for loop. We want to do if and else. And like if you just use the function calling, for example, if you want to do like for loop on like 6 IDs, then you need to call like 6 times. Um, but for coding, you just need to write one line of code. And then we also know, you know, coding about LM is really good at coding. So you can also bring in all of this prior knowledge, internal knowledge on how to do task solving. So that's why we propose to use like code as actions, which is inspired by this paper, Code Act, from this ICML paper.
So, quick
So
question regarding the code. I had two sides. One, is the code always executed locally or remotely? That's number one. And how do we ensure if, as a general purpose, I mean,
mhm,
like things like, AWS, they obviously have their own Lambda and their implementation, et cetera, et cetera. But in the general framework, how do we ensure safety of executing these codes if especially a lot of these computes are going to be client side? And what are the considerations there?
mhm. Yeah, so currently for the web platform, so all the code runs on the AWS instance.
Mm-hmm.
Uh, But for the open source version, basically user can also run it on their own environment, on their own code. Um,
Mm-hmm.
and well, basically we have container, we containerize everything. Um, and at each like after each request is done, we also just clean up all the state, so
Mm-hmm.
it will not interfere with the next request or things like that.
Right.
So yeah, indeed there's probably more security concern that we have not considered yet. But yeah, that's what we have thought so far. Yeah,
Thank you.
cool. Yeah, so that's kind of the overview of our general purpose agent. So it's actually pretty straightforward and simple. It's given, given the question, we do a retrieval, and we'll do the reasonings, and it will compose actions by writing a lot of code. And you can see that you can interleave, have if, and else. You can interleave the specialist tools, and then you can also access to the raw data in a data lake, and also you can call like softwares like this is I think it's gene set enrichment analysis packages, and then it will interleave with observation, and then it will do this adaptive planning. Like once this is done, it will click yes, and then go to the next step, and then it will kind of change as it goes. And so so that's the method, and then we kind of systematically evaluate this general purpose biomedical agent because it's a general purpose, so it requires a lot of curation of new benchmarks as well. So first we use Future House Lab Bench, which is a multiple choice questions. I think we choose the two subtracks where it's very tool dependent. Um, so this one, the first one is called DBQA, which is doing like database queries, and the second one is around sequence QA, which is performing like sequence manipulations. And for tuning the agent, we use 45 questions from these data sets, just to tune the agent. And then we perform it on a holdout test set, and then we're able to see that it has really good performance on human level, and also um, yeah, and then also to quickly introduce the baselines here. The LM here is just base LM. So React is the one without any environment, and this is the coding agent, and this is the literature agent, and this is the coding plus literature agent, and this is the Biomni ablation, where we instead of using code as actions, we use a React like function calling. So you can see that this is kind of expected because we tune on the development set. This is more like a sanity check, and then we hold out a new kind of on a new benchmark. It's also multiple choice questions as humanities last exam, and these are like so there are like 14 I think subfields in the humanities last exam, and in each subfield we select up to 5 questions, and then we let the agent to perform it, and then we're able to see that um, it has the best performance. Our base LLM only have 6% of accuracy, but with Biomni we have around 17% accuracy. And these are like really, really tough, kind of hard questions in biomedicine. I guess that's why it's called humanities last exam. I guess once it's solved, like humanity is saved or something like that. Um, but I think this multiple choice question is still not enough. Um, because like doing an exam is very different from doing like real world research tasks. So that's why we spend a lot of time trying to curate a new benchmark, just for like a realistic um, like a realistic biomedical research. So it's not a multiple choice question anymore. It's like a real task that we ask the agent to do, and then we have the expected output format, and we can check if it aligns with the ground truth. So for some example, we have the variant prioritization. It's basically I have a list of potential genetic variants for disease X, and we want to prioritize what is the top variant. And we have some human expert label for that. And similarly for GWAS called gene detection. So this is from a paper from 23andMe. It have a GWAS hit for some trait a disease. And there are genes, several genes within that locus where this have genome-wide significant if, hits. And then we want to identify what is the likely causal gene. So this requires a lot of reasonings to like close by genes, like picking up which one is the real causal gene. So this requires a lot of database use, also a lot of reasoning as well. And then we have this perturbation screen design, where you want to design a gene panel of 50 genes for CRISPR screen on some new cell types, for example. And this is like a very important target discovery task, where people are given a new cell context, you want to design a screen. So the Biomni can also try to do that by searching databases, doing a lot of literature survey, and running some analysis as well. And then the next two are more bioinformatic analysis. So the first one is a single cell RNA-seq cell annotation. So basically, I have a single cell RNA-seq data set stored at this path. You want to annotate the cell type for each of the cells. And because the annotation is like, because cell type has different granularities, right? So um, we just use a semantic accuracy. We use another LLM evaluator to check how aligned is the human annotation, like the author annotation, compared with the LLM generated annotations. And for the microbiome disease text analysis, we work with a lab to create a new 5 datasets in microbiome. And the bioinformatician from the lab, Minta, who is kind of a like an expert bioinformatician, would perform the same analysis, and then we curate the ground truth datasets, and then we can then compare how the agent is performing, and then just compare how overlap is that. And then we have the drug repurposing dataset task where I have a rare disease access among a list of potential drugs, find me the most likely one for repurposing. And this is with one of my previous work, which is called TXGN, where we have access to a private dataset with from a large scale EHR systems where we can compute the alignment between a drug, sorry, the alignment of this drug treating the disease to the off target clinician prescription patterns. So you can also see that this is a good kind of evaluation metrics for evaluate drug repurposing candidates. And then there's also the rare disease diagnosis, giving a list of phenotypes, a list of potential gene mutations. What is the diagnosis? Cool. So this is the new benchmark that we curated, and this is spanning across different subfields of biomedicines, and we are mainly benchmarking on like 3 baselines. The first one is RMs. The second one is the coding agent, because we observed in the previous one the coding agent actually has the best performance. And then the third one is the ablation on Biomni React. So I think overall, first of all, like with this kind of agentic solution is like much better than the LM. So that's for like almost like 100% of time. And then compared to the coding agent, I think sometimes it's able to perform really nicely, and sometimes it has less improvement, but it's like a 10% improvement, uh, pretty reasonable. But it's up to like 80% improvement. So, I mean 180 as well. But then compared to the ablation, it's relatively similar in several tasks, like 3%, 2.7%. But there's also sometimes can be like big boost. So I think so currently, because for this experiment it's actually really expensive. We have like, because each task has so many examples. So that's why we only do it with zero shot. Like we have not done any tuning. Part of the reason is like we don't have that budget to do the tuning. Um, so it's just like we just apply once, and we were really surprised to see that's such a consistent kind of result improvement over all the baselines. So I think this should be statistically significant that the method is better. Yeah.
Yeah. So there are a couple of questions, I think, if it is a good checkpoint to ask them.
Mhm.
One is regarding the consideration for clinical and patient-related data and tasks, and how Biomni currently or in future envision like accessing data that has, require specific requirements for access. So that's question number one.
I
Let's
see.
start with that.
Yeah, I think the ethics stuff is very interesting. So currently in the at least in the web platform, it's explicitly saying that you should not upload like PHI information, because this is not right, and so I think that's for sure. Um, And then in the local version, probably you can run it. So we are collaborating with Stanford Medical School, and so they have their internal, they call it secure GPT. So they have a way to have PHI information and run GPTs over it as well. And so that's one layer of this kind of data security. But I guess for another is like this around ethics around if the agent is now with operating on human patient data, how, you know, do we need to consider um, if the agent is doing the right thing? What is the risk? What is fairness? And the decent question, I think, is like we didn't answer it in our paper because I think that deserves it on its own papers. It's so complex. Um, and yeah, I think there's a lot of other things that we have not considered in the first version of the paper. And then we just later realized when we talk to many people, for example, like biosecurity. It's like currently we have not do at any red teaming for now. We're trying to do it right now, but
Mhm.
that could also be a bit ethical kind of considerations. But yeah, I think there's plenty of this ethical consideration that we have not considered right now, but we want to kind of address them.
Yeah, and then there's another question. You talked about cell type annotation, and that's a canonical example where, these agent models are capable of using standard ontologies, whereas individual papers may have a lot of inconsistencies.
Hmm.
Again, for cell type, disease, and a lot of other, we have, very standard ontologies. Are there agents to map individual data sets, individual papers to standardized
Hmm.
nomenclature on either one of these to standardize the cell types, standardize the disease annotations, et cetera, et cetera?
Yeah, I think that's a great use case of the agent. So I think I believe we have the cell type ontology as the data. If not, we can easily edit it. Um,
Mhm.
and then yeah, so we can just basically request the agent to map a cell type into the cell type ontology. Um, and yeah.
Harmonized annotations, basically, because that's also one of the bottlenecks in integrating many data sets that were annotated, especially again, like in many papers, we see that the same cell type they use either, contradicting labels or even when using cell type ontology, they use different resolution because it's
Mhm.
very subjective the way the annotations were done. So for
Mhm.
integrating data would be valuable to have agents that harmonize those into a common
Mhm.
vocabulary, common ontology. And that's why I was asking if there's an agent to harmonize
Mhm.
those annotations.
I see, I see. Yeah, I think that would be a very cool use case as well. Yeah, we haven't done that yet, but yeah, it'll be interesting to test the general. Yeah, I mean, we can ask Biome to do it right now, but it'll be potentially we're missing several databases to map the annotations, to unify across many different annotations.
Yeah. Fortunately, again, like you can take it offline, but there is one central ontology database that combined all of them OLS
Mhm.
that we can use.
I see.
They've also asking about an alternative benchmark that how does this compare to quote unquote good comp by a person performance?
Mhm.
How would that compare to like if the benchmark on that like
Yeah, exactly. So then, yeah, I think that naturally leads to our second kind of I guess the next sections is basically we have so because for this one it's just there's just way too many tasks. Maybe there's like thousands of tasks, so it's probably too expensive to compare with a human expert on this. But we do have a few case studies that will delve into more details and we compare with like real human um, expert. Um, so the first example is this Biomni enables this well experiment protocol design. So basically we work with Le Cong's lab. Their input is like we ask a scientist, how can Biomni help you on your day-to-day research? I think the most immediate thing is this cloning experimental protocol design. It's like, so this is a cloning scenarios. I have this plasmid. This is a sequence. It's very long here. I'm just kind of reducted from here. And I want to clone a CRISPR-guided RNA targeting human B2M into this plasmid. Could you give me the final map of the plasmid and step-by-step guidance? And then the Biomni use various different tools like guided RNA design, oligo design, oligo annealing, bacterial transformation, colony screening, and so on and so on. And it takes around like 8 minutes to complete. Um, and then the output is like a detailed step-by-step cloning protocols, you know, and then it also generates some plasmid maps. And then we ask the scientists to follow this protocol and perform the experiments. And then we're able to see that the cloning is pretty successful. And I think here we're not saying that, it's kind of completely making novel discoveries. It's more like a lot of these day-to-day research tasks just cost a lot of time to do. And the Biomni can help them just dramatically reduce the time it will take and as the similar level of accuracy. And yeah, so the scientist from is has a put some nice words. It's like it takes 3 years of training, and even then, biologists spend hours just navigating tools like Snapgene, Edging, and Primary Blast just to design one construct. But biologists can do it in 10 minutes, and the outcome is also correct. So this is where the human level comparison comes in. So we're also just curious, like how good is it, right, on this particular task. So we asked the lab to create 10 realistic, like real world experiment protocol design questions that they also face on their day-to-days. And then on this like open answer cloning scenarios, we then feed this task to LM and also to Biomni. And also we recruit two people. The first one is a trainee, who is a master level Stanford student who have done wet lab experiment before, who have done cloning before. So she knows about cloning. And then we also have an expert who is a postdoc in Le Cong's lab. And then he has maybe probably more than 5 years of training, maybe like even like 80 years of training. And so he's like a real expert in cloning protocol design. And then we have another expert. So after each full of them have finished all of these tasks, we have another expert just look at all of these tasks and then blindly grade the protocols. And the grading is based on completeness, is based on accuracy, and we're able to find that Biomni has pretty similar grade compared to the expert, and much better than trainee and LM. So this basically is a way of showing that we can automate a task to like an expert level. And another interesting thing from this plot here is like we're basically saying this is Biomni could also be a really important educational tools um, to like democratize these expert knowledges. Because previously a entry level PhD, so like a first year PhD student, when join the lab, they probably need to learn from like 50-year postdoc. You probably need to bug it every single day, right? And then you can in the future you just need to bug Biomni. You just say, okay, how do I do this? How do I do that? And so that's a very natural way to democratize knowledge because now you can also get access to the Stanford or Harvard level knowledge um, very easily. Even like no matter who you are, you can just get access to them. Yeah. So that was the kind of on the wet lab side. And we also did a few more kind of case studies on the dry lab kind of computational biology data analysis. So this is work done with Minta and Michael Snyder's lab. Um, so basically, Michael Snyder have a lot. I mean, Snyder lab has lots of this wearable sensor data. It's like continuous glucose monitoring, temperature, and also a lot of activity data as well. And they have around like a new data set, like 30 samples. It's very complex data set. It's like 458 raw Excel sheets. So within a folder, just raw Excel sheets. And then we asked the Biomni just to perform some analysis for us, but just give the folder name and then give some context of what is this data sets. And then it's able to just perform various very complex stuff. And it actually takes 35 minutes, like on its own to finish this entire thing. So it's like really doing stuff, processing stuff, and a very long horizon. And yeah. And it will generate a lot of visualizations. And in the end, it also generates some interesting hypotheses, um, or like some phenomena, some observations. Um, there's some like inter-individual variability on like physiology after meal taking, this kind of a physiological hypothesis. And I think what is the most interesting thing is like, first of all, it's a very complex data analysis. So it took Minta, who's the experienced bioinformatics expert, several weeks, like 2 to 3 hours per day, like 3 weeks, for example, um, and to finish this task. But the agent are able to do it in 35 minutes. So imagine like this is like huge productivity boost. Um, because the now you can also ask the agent to run like 10 analysis at the same time, for example. Then then it just can answer so much more questions for you. So that was on the more physiological data analysis. And then there's also, I guess, on single cell multi-omics data analysis. So this multi-omics actually is a very complex data analysis. That's why we observe that if you just ask to like a very broad question, like I want to analyze this data sets, generate a hypothesis, it does not work. So that's why it requires a more uh, kind of a detailed instructions. So Hanshin here is an expert in single cell analysis. So he was playing around with the agent and he curated a very detailed instructions on what he wants to do to answer some particular questions. And the agent is able to follow the instruction pretty well, and it's able to perform all of these different steps, like running PyStack, running GRM Boost, and use like AU cell, Taxic, and so on and so on. And it generates visualization that's kind of meaningful. And we also manually examine all the execution traces at every step, and they are all like not hallucinated. They are all like following the right thing. And interestingly, it discovers some novel transcription factors like AUTS2 um, and ZFHX3 and PBPX, which is like have show high regulatory activities across multiple skeletal lineages. And these are not kind of reported in the original author's paper. So we're saying this can also a nice way to generate a new hypothesis. So it's not a discovery yet, but it's like a hypothesis that scientists can follow up and run some experiments and so on. And so these are three case studies. Oh, sorry.
So Kishan, sorry, I just wanted to, I know we're coming up on time, but it seems like we've got a couple drug hunters in the chat. So I wanted to ask this question. You have an experiment in the paper about drug repurposing. And
Mhm.
I think people would be interested to hear a little bit more about that if possible.
Yeah, definitely. So we did some we have a benchmarks on drug repurposing. Um, so this one. So I think this basically from so I previously I did a project on drug repurposing. It's basically given a rare disease, we want to identify a list of um kind of a potential treatments from the already approved drugs. And then we're able to see that the Biomni can, for example, doing a lot of literature research and also use our previous models. So, so yeah, so we have a tool which is called TXGN and model prediction, and it will just basically call the tool, and it will retrieve the model kind of top ranked 200 drugs. But it just does not stop from there. It just it needs to do more literature research to double check the if this drug list makes sense and so on and so on. So I think that it uses multiple tools to synthesize a lot of information and knowledges, and then in the end, it will give you a new list. So that's what we have been tested. But I think there should also be other interesting like way to test it as well. Yeah, cool. Sounds good.
I think we have also a lot of questions that are piling up. I don't know if you prefer to finish and then ask the questions at the end or ask them as they come.
Yeah, sounds good. Maybe I can quickly finish since I
Yeah,
also
let's do that. Yeah.
don't have many more slides. Although I was planning, I have 30 more slides, but maybe I'll just finish the Biomni project and we don't talk about the second one. Um, so as we see the Biomni application, there's so much of them. We have, just for fun, we have experimented more. For example, trying to predict ADMET, try to download some random data sets on the internet, like single cell RNA-seq annotations, molecular docking, patristic data analysis, real diagnosis, and so on and so on. Oops. And I think the goal for Biomni is to make every scientist want to use it. So that's why we spend, I think, several a bigger amount of time trying to build a free web platform for scientists to try it out. So I think it's available at biomni.stanford.edu. You can quickly sign up, and we can approve it. I think we should. We're basically approving every day. Um, so yeah, so you definitely feel free to try it out, and then let us know if there's any feedback, and also highlight if there's any cool use case. I think it's just raise more awareness of Biomni, and then more people and we're jumping and then experience the general purpose AI agent. Um, so I was planning to do a live demo, but I don't think we have time. But you can try it now at biomni.stanford.edu, and ping me if you have not got approved. We can get you set up. Um, Cool. Thank you. Now, yeah.
Wonderful. Thanks so much, Kexin. Um, Yeah, we've been trying out Biomni ourselves, or myself at least.
Mhm.
It's a very, very impressive tool. I really encourage people to try it out because I wish I had access to it during my PhD, because I think there's something for older scientists because it teaches you the newer tools in the area. It works based on recent publications, and I think there's something for newer scientists too. Getting set up with these analysis workflows and getting a sense for maybe the implicit tools that it can
Mhm.
automatically discover. So very, very cool work. Um, the one failure case we've run into trying this out
Mhm.
is
Yeah.
that these LLMs can be a bit sycophantic, and
Mhm.
they will generate data that
Mhm.
does not really exist in some
Yeah.
cases. And I was wondering, because I think it's brilliant that you use this implicit knowledge approach for tools
Mhm.
that are so common, but this also runs into the, LLM can kind of do whatever it wants at certain
Exactly.
times.
Mhm.
So have you noticed this, and what do you
Mhm.
think?
Yeah, I think that's a super great point. So so we definitely notice it occasionally as well. So that's why we are implementing a new guardrail system. So like for each step, the LM outputs, we'll have another LM to check, for example, if it's a fake data, if it's simulated data, if it's using like np.random something, if it's like hallucinated, and also if there's some biosecurity stuff. So yeah, so we're now implementing this LM as a job check at each step. And then if it failed, then we'll just basically ask it to redo the thing. So this way, I think it will significantly improve the that it will probably solve the question that you mentioned. Um, and yeah.
Wonderful. Wonderful. So, we have lots of questions that we cannot get to in time, but I believe if Kexin is kind enough, we'd love to have him back to finish with Popper, and then also on KGWAS, one of his other works. Both really interesting, both extending the boundaries of how we do statistics in science. And so, Kexin, amazing talk today. Thanks for being on, and everybody, please go try out Biomni.